Hello. In this video, we will talk about chi-square distribution and its usage. So, simply speaking, chi-square distribution is used to test the category variables' independence or goodness of fit, or the variance of the population. So you can see the name is square in chi-square distribution. So the statistic associated with chi-square test is usually the square of a variable, like the variance and the goodness of fit or test of independence. Both will calculate the squared difference in two categorical variable or in one factor of variable. So if we look in more detail, in the goodness of fit test, you will check that the opposite of the sample data fits a specified theoretical distribution. And usually we will calculate the difference of the observed and the theoretical number, then take a square, then sum together, then get a statistic. And in the test of independence, we also will get the expected and observed values in the association of each of these two variables. Then we get the difference of observed and expected value, take square, then sum together and get the statistic for test. And for the population variance, also, of course, this is the square of the moments of this variable. And the process of chi-square test is usually, we will set up hypothesis of null hypothesis. For example, we assume this die is fair. Then we test and get the experimental data and compare with the theoretical data. And for independence test, we will get the expected and observed. Then we will get the statistic and will determine the degrees of freedom for this test. Then use the chi-square statistic and compare with the chi-square table or the critical region. Then we get the p-value. P-value, which means this is the very small number, which means if we assume the test is null, test is true. So if we assume there is no significant difference or there is independence for the null hypothesis is true, then we get this statistic in the critical region, the probability will be very small. So if we get this very small probability case occurred, then we will have capability to reject this null hypothesis, or we can say the test is significant. So say, for example, if the critical region's probability is under 0.05, so which is the same to say that we have more than 95% of the confidence to say that the null hypothesis is not true, right? So next we will take a look at an example for the test for independence, because this is the most often used case for chi-square distributions test. So suppose we wish to determine whether the opinions of the voting residents in California concerning a new tax reform are independent of their levels of income. So say here there are two variables. One is the income and another is the vote. We will test if these two variables are independent. So we get 1,000 sample from the vote that their data show their low, medium, or high income, and whether or not they favor the tax reform. So the data in this table get total 1,000 observations. So this table is called a contingency table because there are two categorical variables. So the chi-square test tested the independence of two categorical variables, not continuous, two categorical, because For the categorical variables, we can get to the table for observations contingency. So from this table, we can get to the test statistic. And you can see for each value, each of these 6 values, we can get also 2 row margins and 3 column marginals. We get these marginals. Then we set up hypothesis for null hypothesis. Null hypothesis H0 means independence is true. So we say these are goodness of fit and the observed value are not so different from the expected value, right? So the expected value, if this is true, so if this independence is true, the observed value will be very close to the expected value because they are not influenced together, right? So we will represent these letters to say L means the person is low income, M means medium income, and so on. And F is the person selected is favor this tax reform. A means that this person is against the tax reform. Then we can get the marginal probability from the data. This is the marginal probability because we have 2 rows, 3 columns. If we we look at this table. So just using this number divided by 1000. So all the marginals have a marginal probability. So this is observed value, marginal from these margins, and we get a marginal probability for each case of 2 variables. So this is the low income, M income, high income. This is favor, this is against. So next, if H0 is true, and which means the 2 variables are independent, so we should have expected value, right? From these marginal distributions, marginal probability multiplication, so we can get each expected value in this contingency table. So here with low income and favor, this is low income and against, and the medium income and this person also is favor the reform. So this multiplication is based on that these two variables are independent. So we can get 6 expected value. And this marginal probability production, then we times 1000, then get these 6 numbers in squares, which means expected counts if 2 variables are independent, right? So next we can get test statistic based on the difference between observed and expected value from this contingency table. So in the test process, we can use this expression, means observed and expected, then difference take a square, so which means chi-square distribution, chi-square test, we use square, then divided by expected, then sigma together, we can get this chi-square statistic from the data. So if this test statistic, when we think this statistic has degrees of freedom equals R minus 1 times C minus 1. So R minus 1, R is the row number, C is the column number. So in this table, 2 rows, which means here is 1. Then 3 columns, here is 2. So which means this test statistic follows 2 degrees of freedom of a chi-square distribution if if the null hypothesis is true. So if the null hypothesis saying that two variables are independent is correct, then we can get this statistic follows a chi-square distribution with 2 degrees of freedom. So this mechanism should be understandable, right? So if the null hypothesis is true, two categorical variables are independent, then this statistic follow from the data will follow a chi-square distribution with 2 degrees of freedom. Then, under this assumption, if this statistic is located in this region is a very small probability with, for example, alpha 0.05, then the null hypothesis will be rejected because this is a small probability event occurred. So next, we just calculate this number. So from the data, this number is about 7.85. And for a chi-square distribution with 2 degrees of freedom, 0.05 alpha chi-square critical number is 5.991. So which means this is 5.991, but our test statistic is 7.85, is larger than this number. So which means from our test statistic right side, this probability is smaller than 0.05 because alpha is 0.05. So we get a smaller p-value than alpha. Actually, this p-value, our test is about 0.02. So which means we get a very, very infrequently occurred event in our tests. It's about only 1 of 50 chance that this thing has happened. So we just skeptical about this null hypothesis. So I'll say we have 98% of the confidence to reject this null hypothesis. I'll say these two categorical variables of income and their opinions are not independent. Thanks for watching.